G'day, how you going there again? Look, area under the curve. If you watched my previous video, I apologise for the mistake. I missed a negative in there. The correct answer was 12. I got 48. I knew something was wrong, I couldn't spot it. If you look back on that last video, please pick the mistake, follow it through, answer's 12. Anyway, I'll try not to make mistakes here. Still doing area under the curve, but I'm going to do an example like this so we can work out that area using our normal geometric ideas. We can get an answer and then we can check that this is going to work out the same. That way I can confirm that it all works for us. Let's do it geometrically first. This being a trapezium, what I would do is I would work out this and this, average those two, and then multiply by the base here, which would be 4. So, when x is 4, 8 plus 3, that point there is 11. Okay? So that point there is going to be the point 4, 11. Therefore, the area is going to be equal to 11 plus 2 over 2 times by 4 the width here. Now that's kind of neat because we get a bit of this going on. 11 plus 2 is 13 times 2 is 26. So I'm looking for an answer of 26 units squared. Now, a little bit of note on this units idea. We need to be aware that if I'm asked for the area contained under a graph, I must put units on. If it asks for the area under a graph, you must put units on. If they don't give you any units in the question, just put units squared. You're saying to the marker, I understand you're working out an area, you asked me for an area, here you go, units squared. Obviously, if it's got centimetres or something like that, put them on instead. Okay? This question here is not asking for an area. This question here is asking for you to calculate the integral between those limits. Integrals do not have units. Area does. Okay? See it in a similar way to velocity has a direction to it, speed does not. Numerically, they're the same thing, but there's a bit of extra meaning to it. So, area, units, integral, no units. Numerically, they'll be the same. Numerically, they're the same. And they're referring to the same space. Okay? When we get on to other questions where maybe it's not as simple as this, you'll see how they can then vary in different. Rightio, so this one, integrate f of x. Well, here's f of x. So if I integrate that one, aren't I going to get, remember square brackets, and I'll put the limits on the right-hand side now. Integrating that, I'll get x squared plus 3x. Now that's kind of neat because the 2 cancels from the square. Move my limits over, 4 and 0. Now also remember from the previous video that really in there is a plus c. But when I do the upper limit minus the lower limit, that's when that c is going to disappear. Remember this was the formula. Integral of between a and b of f dash of x, the derivative dx, is going to be equal to, well, when we integrate that, we'll get f of x plus c. So it's going to be f of upper limit minus lower limit. Now, the c part of it would be plus a c in here and minus a c, so they disappear. Easy, right, we're here. Let's work this one through, see if you can beat me through. So, put the 4 in. 4 squared is going to be 16 plus 12 minus, well, am I right? Oh, gee, what have I done wrong here? 16, 12, oh, I've made more mistakes. What have I done? Let's double check. I'm worried because this is going to be minus 0 for the second part, which gets me 28. In this case, no units because it's integral. What have I done? What have I done? 2. Oh, that's where I've made my... all good, all good. This is not 2 here, see? This is going to be 3. That means that's going to be 3, meaning that's now 14 times 2, 28. Whew. 2 mistakes in 2 videos. I don't do any editing here. I'll let it go. We all make mistakes. If you're making mistakes, you're learning. Now, clearly, hopefully I already know this, but anyway. What do we got? So 28 28. You can see numerically they're the same. They were. All right, let's do this one. This is kind of there to show you that we don't have to just stick to linear or even quadratic, even cubic. We can do anything. Right, so we're going to integrate sine of x. Now, I'm going to just write a little table here. Remember that when we differentiate, sine of x becomes cos of x, which becomes negative sine of x, which becomes negative cos of x, which goes back here. That's derivative. Okay? So therefore, integral is going to go like this. So we're here currently with sine of x. That's the graph. So we want to integrate. We're going to go to negative cos of x. Negative cos of x. Okay? So this one would become negative cos of x with the limits of pi and 0. Now, key point here with our trig functions. When we're here and we've got a 0, oftentimes you can look and say, not going to make any difference. 0 in there, no difference. With trig functions, don't do the same. Putting 0 in can really change what you're getting because, of course, the cos of 0 is not necessarily 0, but the 0 in here is 0. So just be careful of that. So I'm just going to write this one out a little bit neater here. Minus cos of x, we'll put pi in. Minus cos of 0. Okay? See this as that's the second part. You know the formula that I just had here? That's the second part. That's the f of a. This is the f of b. B being your upper limit, a being your lower limit. And we're subtracting one away from the other. So don't mistake that. Now, let's just flip to our unit circle real quick. Unit circle, there we go. I'm working with cos. Cos is along this axis here. So I'm looking at the cos of pi. That's going to be negative 1. The cos of pi is going to be negative 1. So this in here is going to be equal to negative 1. Okay? Minus, I'll keep that there for the minute. Cos of 0, well cos of 0 is here. That's going to be 1. So I've got plus 1, answer 2. Alright? So this area in here is going to have an area of 2. Now we could probably do a little approximation here and see that we're okay on this because being that it's just the regular sine of x, the amplitude is 1. Right? Now what I could probably do is kind of do this, and look, it's not a great estimation, but if I kind of did that, pi is 3.14 approximately, divide by 2, well actually better still, divide by 2, this is going to be pi over 2, this distance here, isn't it? So 3.14, about 1.6, something like that, right, about 1.6. Can you see that this shape, if I flipped it upside down, it would fit in here. So therefore, that 1.6 comes back to pi, doesn't it? Okay? Because here it would be about 1.6 times 1. That's about it, but I kind of missed some stuff in here, so it looks like it's going to be about right. I think it'll fit about right, and I'm pretty confident on this one. So there's just a couple of examples of integrating functions under the curve. Key points. If you're asked for area, put units on. If you're asked for an integral, this is what we call, there's a good point, this is what we call a definite integral. This is a definite integral. Now, what's a definite integral? Well, a definite integral is one with limits. So I can work out the exact numerical answer. An indefinite integral means I can't work out. So that's the ones where they don't have these, and then you just integrate and put a plus c on. I don't know where it is. You didn't tell me enough information. An indefinite integral, no limits, integrate, put your plus c. A definite integral, limits, ignore your plus c, come to a numerical answer. Hope this one's helped. I hope I don't make too many more mistakes like this in my following videos, but hey, we're all human, I make them as well. You learn when you make mistakes. Good on you guys, hope this helps. Catch you later.